now moving on to aerobic adaptations. So the adaptations to aerobic athletes are different from those of an anaerobic athlete. This is because the demands for anaerobic and aerobic activities are different. We said that anaerobic activities are high intensity and low duration and have an explosive nature, whereas aerobic activities are low intensity but low duration and therefore are not explosive. Aerobic athletes train to improve their cardiorespiratory fitness, which is the athlete's ability to sustain prolonged dynamic exercise. In order to achieve this, the athlete has to improve many different systems such as the cardiovascular system, the respiratory system, muscular and metabolic systems. Other fitness components aerobic athletes may want to improve are their muscular endurance to make sure that they can maintain the same pace throughout a race. For example, like throughout a marathon, they want to be able to continue at the same pace without tiring. Body composition, so again, marathon runners will want to have low body fat, low body muscle, so that it's easier for them to carry themselves, whereas if they had a high percentage of fat and a high percentage of muscle, it'd be harder because they would have more weight to carry. They'd want to improve their VO2 max, and they'd want to have a lower fatigue rate. So they want to try and, again, delay the point at which lactate builds up. So for a marathon runner, lactate is unlikely to build up quite early, but towards the end they'll have more lactate building up, and they will also want to train to learn to resist and tolerate the lactate that's built up in their muscles. Aerobic athletes are likely to use endurance training, such as continuous training. By training continuously, it can lead to long-term adaptations of an increased maximal endurance capacity, a higher VO2 max, which is your maximum rate of oxygen consumed during exercise, and submaximal endurance. Endurance training can also come with lots of benefits. It helps to reduce your chances of getting many health problems such as obesity, diabetes, and coronary heart disease, as it strengthens the heart, which we'll talk about later. And if there is fat, they burn it as energy, so it helps for weight loss as well. The graph on this PowerPoint shows us the athlete's VO2 max before and after a bout of endurance training. So it shows us that by training for endurance events such as marathons, athletes' VO2 max will increase. Therefore, it's more helpful for their next race. As you can see, before training, the VO2 max is shown in blue and it's shown in red post-training. When training aerobically, many long-term adaptations are likely to take place. For example, a triathlete who has been training aerobically is likely to have athlete's heart. This is where the heart becomes enlarged and therefore meaning that the resting heart rate is lower. This resting heart rate is caused by hypertrophy of the heart, which is where the myocardium of the heart strengthens and enlarges. This can be seen on the image in the bottom left. Having a lower resting heart rate means that the athlete has an increased heart rate range, and when the resting heart rate decreases, it then increases the filling of the heart at rest, meaning that the end diastolic value will also increase at rest. Cardiac hypertrophy can also lead to a larger stroke volume. We know that to increase the cardiac output, volume of blood pushed at the heart in 1 minute, we must increase our heart rate and stroke volume. The increased size and strength of the heart after training means that the athlete's stroke volume will increase, allowing more blood to be forced out of the heart per contraction, and therefore more blood reaches the working muscles, quicker. An increased stroke volume can also lead to an increased volume of plasma in the blood. This means that there is an increase in the athlete's end diastolic value, meaning that the athlete can then increase in preloading. This increase in plasma also increases the blood's viscosity, meaning that it's easier to move around the body, so the heart doesn't have to work as hard during their performance. During aerobic training, it is likely that athletes' hematocrit value will increase. This is the percentage of red blood cells in the blood. An increase in red blood cells concentration means that there is more hemoglobin present, allowing a higher volume of blood to be carried in a higher volume of oxygen to be carried in the blood, and therefore to the muscles. Aerobic training can also lead to capillarization, which is increased number of capillaries. This means that there is an increased surface area and therefore makes it easier for oxygen and carbon dioxide to diffuse from the muscles. Endurance training can also lead to a decrease in cardiac diseases such as coronary heart disease. The graph shows us an athlete's heart rate after performing steady state exercise for 20 minutes on a exercise bike. We can see that their heart rate starts off at about 75 beats per minute at rest, which is good, and then increases before the test starts, showing that they had a anticipatory rise due to nerves. We can then see that their heart rate slowly increases up to about 115, 111, which tells us that they are working in their aerobic threshold. Some respiratory adaptations for aerobic athletes include an increased ventilation. Ventilation is found by timesing your breathing rate, which is the amount of breaths taken per minute, and timesing that by your tidal volume, which is the volume of air moved in and out of the lungs per breath. This is because there is a more efficient tidal volume, which leads to alveolar ventilation. Alveolar ventilation means that there is an increased surface area, meaning more space for oxygen and carbon dioxide to diffuse through, meaning that it is faster. Endurance training also increases an athlete's VO2, meaning that their oxygen deficit decreases and therefore their recovery and their EPOC will also decrease. The more aerobic training you perform, it's then less likely that you'll contract a lung disease, such as chronic obstructive pulmonary disease. Another respiratory adaptation includes an increase in your arterial venous oxygen difference due to an increase in oxygen extraction. The increase in oxygen extraction is because of an increase in oxidative capacity. Lastly, hypertrophy of the cardiac muscles, so of the diaphragm, of the intercostal muscles, and of the lungs themselves, and it makes it stronger, so therefore they require more oxygen per breath, meaning that their breathing becomes more economical as they don't have to work as hard to get as much oxygen. For the neuromuscular system, there are also adaptations that can take place when performing moderate intensity training. So you will get an increase in the size and the number of type 1 muscle fibers that you recruit. It's likely that you will also have to use your type 2A muscle fibers, although you're more likely to recruit your slow oxidative muscle fibers. There is also, as we said earlier, there was an increase in the number of capillaries. So this number of capillaries means that there are more individual capillaries supplying each muscle fiber, and therefore it's easier for oxygen to diffuse into the muscles, making it easier for the athlete to perform. There is also an increase in myoglobin content from around 75% to 80%, again meaning that more oxygen can diffuse into the muscles from the blood, meaning it was easier for aerobic exercise. Another adaptation is that there's an increased number of mitochondria. So mitochondria is where aerobic respiration takes place. So obviously an increased number will increase energy and will make it easier for the athlete to produce energy. There is also an increase in the activity of the hormones SDH and citrate synthase, which with training enhances glycogen sparing. Yeah. Although most aerobic athletes use moderate intensity training, sometimes HIIT training, which is high intensity interval training, can also include some benefits. So HIIT training is more time efficient, and some of the adaptations associated with aerobic exercise can take place from HIIT training. For example, mitochondrial enzymes, cytochrome oxidase, increases after HIIT training compared to moderate intensity training where not as much or none is produced. So it may be more useful for the athlete to perform HIIT training. And now we're going to talk about lactate thresholds of aerobic athletes. So it's likely that these athletes will have a higher percentage of their VO2 max, which we know from earlier, and this leads to a decrease in lactate production. This means that the athlete's muscles will be able to continue for longer, and it won't hurt as it would in anaerobic exercise, and there's an increase in the clearance of lactate. So when lactate is produced, it is removed from the body quicker. This allows aerobic athletes to train at a higher intensity without accumulating lactate, which can be a huge advantage for aerobic athletes. Aerobic athletes use their aerobic energy system, but before they use it, they must use their ATP, ATP-PC, and their glycolysis system, as they're the fastest and the first energy system to be recruited. Mitochondria produce energy, so when there are more mitochondria, that means more ATP. And more ATP means more energy, and that means that the athlete will be able to work harder. When there is more myoglobin in the muscles, this means that there is an increased amount of oxygen to the muscles. And the muscle fibers we use, as said before, are our slow oxidative muscle fibers. And these muscle fibers tend to increase in size, and the amount of these slow oxidative muscle fibers increases as we use them more than we do our fast glycolytic muscle fibers or our fast oxidative glycolytic fibers. During aerobic respiration, many of the steps involved